All right, so there are 5 stages in solving problems of AI. As we have said yesterday, the first stage is to define the problem. Initially, what we do is we define the problem. So, whenever a problem arises, okay, the agent must initially define the problem precisely. Precisely in such a way that the particular state space can be represented through it. Okay, when I say state space, okay, I mean to say that all the set of all states reachable from the initial states, that is called state space. Fine. And the second stage is analyzing the problem. You have to the problem should be carefully examined before solving any kind of AI problems, and in doing so it can have immense impact on the resulting solution. And the third step is identifying the solution. This generates reasonable amount of solutions to a given problem. um, After the problem statement is converted to a state space, okay, all the possible states that are generated in the state space, um, they are chosen, okay, which can be fitted to the current problem. Those uh, possible states which can be fitted to the current problem, they are chosen, and the rest are ignored while dealing with this particular problem. And the fourth step is to choose the solution. After generating all the possible solutions, you choose the optimal solution. Okay, this is done on the basis of the results produced by the respective solution. And the last stage is implementation. Once you identified the solution and choose the optimal solution, you started with the implementation. Okay, that's all about this. Next, we have problem solving methods. Others are forward reasoning and backward reasoning. We won't do this in a very detailed manner because in the upcoming chapters we have separate the chapter for this reasoning itself. So we'll do in a more detailed way in that chapter. Now we'll just have an overview and simple example, basic ones on what forward reasoning and backward reasoning is. Okay, so um, forward reasoning, this type of reasoning, it starts from uh, the known facts. Okay, you would be given some facts, okay, and it triggers all the rules whose premises are satisfied, and it adds their conclusion to the known facts, and this process repeats until the problem is solved. And the approach is called data driven approach. Why it is called data driven approach? Because we reach the goal, okay, we reach to the goal using the available data. That is why it is called data driven approach. And as I have said, the process starts with new data and facts, and the aim is to determine the result followed by some sequences. um, the approach that is followed here in forward reasoning is bottom up approach. Okay, so let me write down here in this board: forward reasoning. Okay, so in forward reasoning, um, let's say you are given some facts. This is fact number one. This is just a block diagram to explain forward reasoning. Okay, you have fact two, fact three. You have, let's say, you have n number of facts. Okay, and then fact four. On combining these two facts, okay, you commit a decision. Let's say decision one. Okay, and when you combine these two facts, you come up with another decision, that is decision 2. Okay. And after that, on combining these two decisions, okay, which you derive from the initial facts, if you combine this again, you'll come to the final decision, the final result. That's how forward reasoning is solve. Now, it may be hard for you to understand using this block diagram. I'll just explain it more precisely. See, here, as you can see it in the block diagram, you start from the initial state, and it uses facts to make conclusions, right? And such kind of reasoning, they are employed in export systems and production rule systems. Okay, let me explain this forward reasoning. For example, let's say you have this A, okay, and this is the starting point. Okay, this is the starting point, and then you have some facts given to you. The fact is A. If A occurs, then B happens. Okay, then this is the fact given to you, and you the thing that the goal that you that the objective that you are supposed to do here using forward reasoning is you have to achieve this decision B using this starting point, using this given fact. Okay, you have to prove B. Okay, okay, let me make it in another way. Let's say that A, which I have said was wait, just wait. A to B. This was the fact that was given to you. And let's say that if a person is running, okay, if a person is running, he will sweat. So this is the given fact. Okay. Then the starting point, that is A, would be Tom is running. Okay, Tom is running, and you are to prove that Tom is sweating using this given fact. Okay, this is given to you. Okay, this initial is given to you, and you are to prove Tom is sweating using the given fact. This is the fact. So how will you prove that Tom is running? So Tom is running, and if you substitute Tom here instead of a person, if Tom is running, then you will sweat, right? Tom is running, Tom is running, that's the given statement, right? So you can conclude that Tom is sweating. Let me give another example. Question can be framed like derive forward reasoning using non-facts to prove Tommy is black. Okay, there will be given facts, and you have to prove that Tommy is black using the given facts. Fine. So what are these facts? I'm going to write it in the next slide. Okay. So the facts that are given to you are, number one is if D barks, okay, and D eats bones, then D is dog. Okay, and the second fact given to you is if V is cold and V is sweet, then V is ice cream. Third, if D is a dog, then D is black. The fourth, if V is ice cream, then it is vanilla. So these are the given facts to you, and the statement that is given to you is that Tommy barks, okay, and Tommy eats bones. So what was the question that we have here? The question is that using forward reasoning, okay, you have to prove Tommy is black, okay, provided the known facts. So these are the known facts to you, which I have written it in the board. Okay, so now how will you do? From fact 1, okay, it is clear that if you substitute D as Tommy, okay, if Tommy barks and Tommy eats bones, then Tommy is a dog, right? See, these are the given. Tommy barks, Tommy eats bones. If you substitute D as Tommy, it is if Tommy barks and Tommy eats bones, then Tommy is a dog, right? So your first conclusion uh, from the two facts, from this given fact, is that Tommy is a dog, is a dog, right? This is from this is inferred from fact number 1, right? See, if you substitute D as Tommy, then this is the inference. So I'm just writing down the inference. Okay, now you have this Tommy is a dog, right? Now if you look at the other facts, the remaining facts, which is suited with this given to you, Tommy is a dog. You can find somewhere here in the facts dog here, if D is a dog. So you can substitute D as Tommy here again, right? So if Tommy is a dog, then Tommy is black. So here you came to the conclusion that Tommy is black, right? And that's what you want to prove, right? What was the question? The question was to prove Tommy is black, right? So you have already proved Tommy is black, right? So I hope there is no issue with this. Now let's go to backward reasoning. Yeah, so let me just go back to this block diagram. See, as I said, using fact 1 and fact 2, you come up with decision 1. Using another fact 3 and 4, you come up with another conclusion, right? Another decision. And you combine these two decision and you come up with the final conclusion. So same way, that's what we did here. This is fact 1, right? Fact 1, you have this and this, you combine this and you come up with this decision 1. This was your decision 1. And then another thing, this was your decision 1. And then you combine this decision 1 with this fact and you come up with this final decision which you want to prove, right? Okay, so next is backward reasoning. Okay, this backward reasoning, it starts with the goal. Okay, in case of forward reasoning, you are proving the goal using the known facts, right? But in case of backward reasoning, you are going to start with the goal. The goal is known to you and it is going to work backward. Fine. And this type of reasoning is based on modus ponens inference rule. I am not going to do this in detail. You can refer to your books of discrete mathematics, or you can search it online. What are the formulas of modus ponens? Okay, and it follows top-down approach. This is the opposite of forward reasoning. And in this type of reasoning, the goal is broken down to sub goals. Okay, to prove the facts true. Okay, you have to prove that the facts are true. And why is this backward reasoning known as goal driven approach? Is because the list of goals decides which rules are selected and used. Okay. Okay, so let me explain backward reasoning again here in slide number 18. Okay, backward reasoning. Okay, so in backward reasoning, let me also write that block diagram for this. Um, it works in a reverse way, right? You have n number of facts, fact 3, fact 4. Um, okay, so in this you are given the goal, and then from the goal you are trying to prove the facts through. Decision 1, this is decision 2. Labels are same, you just have to change the arrow. Okay. So this type of backward reasoning, they can be used in diagnosis of problems, or it could be used in debugging problems, and also for prescription applications. Okay, so um, let me give an example of backward reasoning. Um, you will be given this, that is the goal, and this is the fact that is used to achieve the goal, right? And A is the initial state. So let's say B, that is Tom is sweating. Okay. Let's say B denotes Tom is sweating. This is the goal node, right? And the rule is if a person is running, he will sweat. This time it's given in a reverse way. So Tom is sweating. If a person is sweating, that means he's running, right? So your answer would be Tom is running, and this is A, right? Denoted by A, or whatever you are taking. Okay, that's all about backward reasoning. There is one expert system called Mycin, which make use of backward reasoning. Let's see a little bit about this. Mycin, this is a real life example of how backward reasoning works. Okay, what is this? It is an early expert system, or you can say it's an AI program for treating blood infections. Okay, you can say AI program for treating blood infections. This work began in 1972, okay, where it started at Stanford University. Uh, that's in California. Okay, so what this expert system is trying to do is that it tries to attempt to diagnose the patients based on the symptoms, okay, and the test results that it gets from the medical reports. So what it does is, in this expert system, um, diagnose patients based on the symptoms and medical test results. So this system is suitable for patients who have bacterial infection. Okay, suitable for patients with bacterial infection. Though it is used for patients with bacterial infection, the specific infection, okay, is not known. Okay, and this system, uh, okay, just write one more point on this. How it does is it gathers information related to the symptoms and the history of the patient, which was already mentioned here. And after gathering all this information, it started to analyze um, and find out and tries to find out the bacterial infection. Okay, so for example, if you have some suitable sequences like um, let's okay, I won't write it down, I'll just say it. The patient, let's say you have some facts like um, the patient has a bacterial infection and the patient is vomiting. Okay, and the patient is also experiencing diarrhea and severe stomach upset. So using these facts, um, I mean, using this available data, you can conclude that the patient has typhoid, which is a salmonella bacterial infection. You can, I think it's there in the reference that is given to you. If you don't find this there, you can Google it and see a little more information about this. Okay. Okay. So one more that we have to do is let me go back to slide number 1. All right. I hope everybody has already captured this. I'll just clear it. So yesterday I said that we'll discuss the basic problem solving methods, and I have listed around 4 points, right? Maybe we can do a little bit about one point, that is state space search. Right. Okay, so let me clear this. State space search. Basic problem solving methods, and today we're going to do for state space search. As I have said, I'll repeat it again. What is state space? State space is set of all states reachable from the initial state. Okay, what is state space search? It is the application of the operator to a state and subsequent transitions to next state until the goal state is reached. Okay, so um, you can write down state space search is the application of the operator. And what are these operators? These operators are nothing but you can either move upward, downward, left and right only. Okay, to the state you're going to apply these operators to each state and the subsequent transitions to the next state, And how long you're going to perform this operation? Until you find the goal state. Until the goal state is achieved or reached. So in such kind of question, you are going to be given one state, initial state, and the goal state. So let me give one problem. One example of this state space search would be a puzzle problem. For a 3 by 3 board. Okay. Uh, yeah. This is the initial state that is given to you. Let's denote it by S. Okay. And you are to achieve this goal state using this given state to you. Okay. Okay, so what is the initial state? The initial state is, let me write it using different colors. 1, 2, 3, 4, 8, 7, 6, 5. These are the given datas. And then you are to achieve this goal. You have to make this initial state to be exactly the same as the goal state. 4, 5, 6, 7, 8. Okay. If you look at these two states, they are entirely different, right? And using the operations that you have, that is, either you can move up, down, right, left. Using this operation, you are going to make this state like this. So how will you do that? Okay, so this can be represented by, this initial state can be represented by 1, 2, 3, comma 4, 8. The empty cell can be written as 0. Okay, and then you have 7, 6, 5. So that was the initial state. Okay, now which operation will you perform? Will you use upward, downward, or right or left? Now, so what you can perform this operation on the empty cell. Okay, so can you move the cell right way? No, you cannot move. You can either move left way, up way, or downward now, the available option to you. But if you look at the goal state, 3 is here and 3 is at the right place. So it's not required to move upward. If you look at the left side, 8, you can move it on the left side as well. Or you can move this downward as well. But let us look for that. Let's apply for downward operation. Okay. So now let me do this downward operation. If you perform downward operation, you will get this 4, 8, 5. 5 will move upward now, right? The empty cell comes downward. 7, 6. Okay. Now, keep on comparing the initial state with the goal state. This is perfectly fine. The first line, 1, 2, 3, 1, 2, 3, 4, 5. 5 is not there at where it's supposed to be. But right now you cannot move that. You are supposed to move this empty space only. So we'll look at this. And where can you move this? You can move this at the left side or at the upper side. Downward and right, you don't have any other cell, so you cannot move. So where is it supposed to be moved? You are going to move this on the left way, right? Because this recently you have moved this 5, so you cannot move it back to the initial place, right? So you're going to move this on the left. Okay, when you move this to the left, what will you get? You will get 1, 2, 3, 4, 8, 5, 7. This has come to the left, right? And then 6. So this is your current state. Now compare it with the goal state. 1, 2, 3 is fine. 4, 8 5. This is not fine, right? This is not fine. And 7 6. So here you can either move the empty cell to the right side, left side, or upper side, not down side, because there is nothing below, right? So if you compare it with the goal state, 8 is down here. So if you move this cell upward, 8 will come downward, right? So this is more appropriate. So you will move um, this cell upward. Okay. If you perform up, if you apply up operation, then you are going to get this in the next state. 1 2 3 4. This is dash 5 7 8 comes downward. Okay, 6. Please don't get confused. I'm moving this empty cell, okay, not this thing. That's why this is moving upward. This empty cell is moving upward. That's why I'm writing upward. Okay. Now compare this current state with the goal state. You have 1 2 3. um okay, so 7 8 6, 7 8 6. It's not fine yet, right? The cell, the empty cell is here. So right now, what is the most appropriate move that you can make? If you move this to the right way, 5 is going to come here, right? So that is more appropriate right now. So let's move this empty cell to the right side. So perform right operation. What is the next thing that you're going to get? You're going to get this. You will get 1 2 3, and then 4 5. This comes at the right now, and below you have not performed any operation. 7 8 6 as it is. Now again compare this current state to the goal state. 1 2 3 is 5 fine. 1 2 3 is fine. 4 5, this has to be, something has to be here. What is that? 6 has to be here, right? If you look at below, 7 8, 7 8 is fine. 6 you can move upward. So it's, if you can take this downward, right? This blank cell to the down. So if you perform down operation, you'll get the final goal, final state. I don't have space here, so I'm writing it in that way. Okay, if you have ample space, then you can keep on following it downward, downside. Okay, wherever space it is, you can just write down. Just the arrow has to be correct. 1 2 3 4 5, and this cell comes downward. That means the below number comes up. 4 5 6 7 8 dash. Now compare this current state with the goal state. It's same to same, right? So done. You have achieved your goal. You have to stop here. But you also have to represent all these boxes in this format. Okay, this is the initial state is represented as S0. This will be S1. This will be S2. This is S3, S4, and then S5. Okay, and so the total path course is 5. Okay, why? Because you have moved 5 times, right? You have moved from S1 to S5. So the total path cost for this problem is 5. Let me just write this. S1 can be written as 1 2 3, then next line 4 8 5 separated by comma, and then 7 6. This blank cell can be written as 0. Then you close with square bracket. Same way you are going to do it for S2. This. Okay, so yeah, I think that's all for today. You can do one example. I'll give you one question which you can solve. Solve this using this state space search method. Okay, the initial state given to you is this 2 3 4. You are going to have many solutions, okay? Um, but among all these available solutions, you are to choose the one with the optimal path, that is taking less cost, okay? 8, 7, 6. This is the initial given state, and the goal state would be 1, 2, 3, 8, 4, 7, 6, 5. So I said that this empty space can be moved in different directions. You can move downward, upward, left, right. Okay. So you will try for all these possible moves. Okay. You'll try for all these possible moves. For this particular move in this direction, you'll go keep on doing it here. Okay. And calculate the total cost path. And for this as well, you can calculate the total cost path. This will come under this moving in this direction will come under this, and you can perform the operations. And among all this, okay, possible solutions, after calculating the total cost, you have to choose the minimum one, okay, and you are to write that, you are to choose that one, that optimal cost, and write the different states. This will have different states, this will have different states, this will have different states, okay. So you have to choose that optimal path and write that one. That's all for today. Anything you have to say or any query, you may. If not, then that's all for today. No doubt.